Hello, everyone. Good afternoon. Welcome, welcome. Glad to see you as usual. Thanks for having your cameras on. I have gotten a sense that I know some of you throughout this year, and that's really fun, and I really appreciate that. So thanks for reaching out to me and having your cameras on and keeping these conversations going. I really appreciate that. As I said in the chat, this is our last day of new material. So we'll be finishing our coverage of nuclear chemistry here today. Next week will be reserved for a review for the exam on Monday. And then on Wednesday would just be a general question and answer session. You can ask me questions on anything, problem sets, quizzes, whatever. And then Thursday, as you know, is exam 3. It'll open at 10, close at midnight. It's a 70-minute exam. I'll send you all the details on an email at the end of the week. And then Monday, of course, the following Monday, which is a week from this coming up Monday, is the final exam. Okay. I went through and I updated grades in the sense that I went through and I dropped your lowest problem set. So your lowest problem set should now be dropped from your grade. I also dropped your 4 lowest before and after assignments, pre and post lecture assignments. So those should be now dropped from your grade. So really, the only thing missing from your overall grade then at the moment is this next problem set, which is due on Friday, and then the 2 exams. That's all that's left in terms of credit for the, oh, and maybe a couple labs that still need to be entered. Okay, so what you're seeing on Canvas should be pretty up to date and now includes those things that I said I would drop. All right, good. Do you have any questions for me before we get going today on finishing up our coverage of nuclear chemistry? All right. No pre-lecture assignment, correct. The only assignment left on mastering is the problem set that's due this Friday. Anything else? Okay, well, you can always put a question in the chat or interrupt me as we're going along here, and I'm happy to answer any questions. But if you remember at the end of last time, we were talking about nuclear fission, right? So remember that nuclear fission is you take a heavy atom like uranium, you bombard it with a neutron, and that causes the atom to become unstable and split in 2, okay? And that process also emits a large amount of energy. We'll see the source of that energy here in a little bit. And that process is also capable of undergoing a chain reaction. What does that mean? That means if you initiate fission in 1 atom, it can produce 3 neutrons, which can initiate fission in 3 others, and so on, right? In order to have this chain reaction happen, you got to have what's called a critical mass, a minimum mass of uranium-235, and that's an isotope of uranium. That's not the main isotope of uranium. So you have to have what's called enriched uranium. Uranium-235 is only like 1% of all. So if you have a naturally occurring sample of uranium, only about 1% of it is uranium-235. So you have to enrich that uranium, which means increase the amount of uranium-235 and separate it out from the uranium-238. And then that kind of uranium can undergo, can achieve a critical mass and undergo fission. We saw that that could be used to build bombs, but it could also be used to generate electricity, all right? So how does that happen? Basically, in a nuclear reactor, what you have is a controlled fission reaction, all right? So it's the difference, say, between gasoline exploding in a tank, right? That's kind of like a uncontrolled explosion, or gasoline burning in an engine, right? Where you control the process and therefore can harness it to do what you want, all right? So it turns out most of the time, most of our electrical generation facilities generate electricity from, you need a heat source, right? So that heat source can be the combustion of coal, for example, or the combustion of other fossil fuels like petroleum, right? But it could also be nuclear fission, all right? And what happens is the nuclear fission creates heat. The heat boils water, creates steam. The steam is forced through a turbine on a generator, right? And then the generator generates electricity, right? Which you and I are using right now, right? So the key here then is this nuclear core and how that works and how you can create a controlled fission reaction as opposed to one that's out of control. So in order to control it, the way they do this is they have in the core, there's all these fuel rods. So these are enriched uranium rods, right? That can undergo nuclear fission, all right? And they have uranium-235 in them, not pure uranium-235, it's enriched uranium, which means it has a higher percentage of uranium-235 than normal uranium. It's not enriched enough that it can really produce a nuclear bomb. That's important to understand. Some people think, oh my gosh, a nuclear reactor can explode like a nuclear bomb. That is not true. A nuclear reactor can never explode like a nuclear bomb because the uranium used for nuclear power generation is not as enriched as the uranium as what you need for a nuclear bomb. Okay, so that's not a real issue. But the main thing is that what you have in this core is you also have these control rods, and this is the key to controlling the reaction. Okay, the control rods are usually made of cadmium or some other good neutron absorber, right? So when the control rods are up, right, neutrons can get from one of these fuel rods to another as the fission occurs, right? And that allows the reaction to continue to move forward, right? It allows you need the neutrons to be able to find other uranium atoms in order for this to continue, right? But if these control rods are put down, they stop the neutrons, right? And therefore stop the reaction. So these control rods are very carefully lowered and raised, right? To maintain the level of reaction that is necessary, right? To produce the amount of heat that's necessary. If the core starts getting too hot, what do? The person who's controlling it, right? Drops the control rods down in between the fuel rods and the reaction slows down, right? Because there's not as many neutrons not as many neutrons can reach other uranium atoms to keep the reaction going, right? If the reaction starts to get too cold, you lift the control rods up, right? And that allows the neutrons to get through and induce fission in other uranium atoms. Does that make sense, how that works? Let's see, Taylor, did you have a question?
Yes. So are they always reacting? Or do they only react with themselves or each other? Sorry, each other.
I'm sorry. What are they always reacting? Is that what you said?
Yeah, so the control rods come down.
Yes.
And that stops the reaction of each other, right? Like
Right.
them throwing neutrons at each other.
Correct.
But do they throw neutrons at themselves? Like, do they react with themselves or only with others?
Well, remember that so if we go back to this picture, right? Once a particular uranium atom undergoes fission, it can't undergo fission again, right? But it produces 3 neutrons, right?
Okay.
And then so the question is, do those 3 neutrons, do they have the ability to induce fission in 3 other uranium atoms? Right? And what the control rods do, imagine a control rod, if you let's say the control rod is right here where my arrow is, right? Where my mouse is.
Mm-hmm.
Lift the control rod up and the neutrons can find other uranium atoms. Put it down and it stops that process.
Oh, so it has to go across other rods.
Well, I mean, it has to go across other rods to have what's called the critical mass, right? So one rod by itself wouldn't have a critical mass. One rod by itself, there is fission happening in each of the fuel rods, right? And some of the uranium atoms in a fuel rod can induce fission in other uranium atoms in that fuel rod. But by itself, it's not enough for a critical mass. It needs the other rods.
Okay, I forgot about the critical mass part. Yeah, that makes sense now. So each one is not critical mass, but together
Correct.
they can
Correct.
add up to that critical. Okay,
Exactly
that
right.
makes so much sense.
That's exactly right. So that's
That's
why these
crazy.
control rods are so essential, right?
That's so crazy. All right,
Yeah,
thank you.
it's pretty amazing. Sophia.
And like, I guess every once in a while they have to change the fuel rods because that uranium that undergoes fission no longer
Correct.
used.
Correct. Once they're spent, they have to be changed out. So I think I don't know what the normal schedule would be, but it lasts months to a year, right, before they have to switch it out.
Okay.
Remember
I
what we
guess
said
it's
last
like
time?
cool.
If you had a fuel rod the size of a pencil, right, for nuclear fission, and your car was powered by nuclear fission, you could drive your car for 20 to 30 years on that much fuel, right? So it's very,
You
very
said that
concentrated fuel.
you said that we still like you need to have a car that uses more energy than our cars
Right.
do,
That's
right?
so I'm ignoring the idea that you need a critical mass. You can never really have a nuclear powered car because the car doesn't have enough power requirements. We do have nuclear powered ships in our Navy and nuclear powered submarines, right? And these vessels stay out at sea for many, many months at a time because they have enough fuel to go for years. Okay, good questions. I'll get to the waste elements here in a minute. So just a little comparison. 50, so a nuclear power plant would use about 50 kilograms, about 100 pounds of fuel a day to generate enough electricity for 1 million people, right? And there's no air pollution associated with it, right? Because there's no carbon dioxide, so there's no global warming associated with it. No nitrogen oxides or sulfur oxides, so no acid rain. None of these environmental problems that are associated with fossil fuels are present in nuclear power. A coal burning power plant, by contrast, would need 2 million kilograms of fuel per day to generate enough electricity for 1 million people. So that's, many more times, obviously much more of a volume of fuel compared to this, if you can make that comparison. And it produces nasty things like nitrogen oxides and sulfur oxide that add to acid rain, produces carbon dioxide that adds to global warming, right? And so there are some advantages to nuclear power. There's also some concerns about it. You can have a core meltdown. What happens there? Well, if you lose water from the core, the heat can actually melt the core. And there was a movie made, I don't know, probably 30 years ago now, 20 years ago, called The China Syndrome. And the China Syndrome is about this sort of melting of the core because the core gets out of control. So if somehow, right, this system were to fail and the reaction were just to continue to happen unabated and uncontrolled, it would get so hot that nothing could contain it. Now, it wouldn't explode like a nuclear bomb. Let's be clear about that for the reasons that we already talked about. But it would get so hot that nothing could contain it. So this movie called The China Syndrome was based on the idea that it gets so hot that it melt all the way down through the core, down into the earth, and all the way to China, right? That was kind of what the movie was based on. That's why I got it. That's where it got its name. That, of course, wouldn't happen. But we have had accidents. Chernobyl, for example, is one. Chernobyl in the former Soviet Union, where they were doing an experiment to try to reduce the life on some increase the lifespan of some emergency generators that they had. And while doing that experiment, they had to shut down all the safety features of the core, and the experiment didn't really work. And so the core heated up, and there was a partial meltdown of the core, and it scattered radioactivity out into the environment. It killed about 30 people in the immediate aftermath that came in and tried to stop it and salvage what was going on. The other big accident that happened was at Fukushima Daiichi power plant, where they had a tsunami that came in and also created similar problems with the nuclear reactor there. Okay, and again, some of the radioactive elements got into the environment, right, which is what we don't want. So that's one problem with nuclear power. The other problem is waste disposal. So that waste is itself highly radioactive, right? And what do we do with it? Well, so far we haven't got a good, we haven't found a good solution for that. Well, we actually have some decent solution. So for example, you could put this radioactive waste in containers and bury it in the side of a mountain that has very stable geology, right? And that's been proposed, but political problems have prevented a site like that from being developed. So right now, unfortunately, most of the waste is stored on site at the nuclear power plant. It's not a huge amount of waste, right? Because it's not a huge amount of fuel, right? Because the energy is so concentrated, all right?
Hey Tro, if the waste is highly radioactive, is there like any way to reprocess it for like more energy use or?
There is some possibility of that, but it's not super easy. But yes, you can do that. And that is currently not happening. I don't know if it's cost effective, but it is possible. There's this is the facility was at Yucca Mountain, Nevada, that they're trying to get this thing passed, but so far, no, it hasn't really happened. Okay, so, what's the bottom line? The bottom line is we have, I don't know, we have a certain amount, we have about 10%, I think, or a little bit under 10% of our electricity is generated this way through nuclear power. It doesn't seem politically like advantageous right now, at least in our current environment, for us to build more of these things. So we are where we are. They may play a role in the future. They may not. We'll just have to wait and see, right? It just depends on how these other, the main thing is that the cost of things like solar power and wind power have come down so much, so dramatically, that now we're really focused on those technologies, and those technologies have really been working. So that's what's really growing right now in terms of alternative fuels, is mostly solar power and wind power. Okay, good. Well, where does all that energy come from in nuclear fission? Well, it comes from it comes from mass being destroyed. So remember last semester we said there's this law of conservation of mass, which says in a chemical reaction, matter is neither created nor destroyed, right? Well, that's true, but in a nuclear reaction, that's not the case. And remember last semester, you might have played around with this. If you add up the masses of all of the particles in a nucleus, those masses do not add up to the mass of the nucleus. In other words, the mass of every nucleus is lower than the masses of its separate particles. Okay? And that's because when the particles join to make a nucleus, they actually lose some mass, and that mass is converted into energy. All right? And the equation that governs that is Einstein's equation, E is equal to mc squared. So E is energy, m is mass, and c is the speed of light. All right, so for example, here's the fission reaction we looked at just a little bit ago. All right, uranium and a neutron goes to form these particles, right? This barium, krypton, and 3 neutron. If you add up the masses of these particles on this side of the equation, you get a mass of 236.05258 atomic mass units. If you add up the masses on this side of the equation, you get 235.86769 atomic mass units. Notice that the products are lighter than the reactants, right? The products are lighter than the reactants. You've actually lost this much mass, right? In the process. So we can figure out how much energy that is, right? So E is equal to M, 3.07 times 10 to the minus 28 kilograms, right? Times the speed of light, 2.9979 times 10 to the 8th meters per second squared, right? And that's equal to 2.7593 times 10 to the minus 11 joules. And you might think, oh, well, that doesn't sound like very much energy, but that's the amount of energy for each nucleus that undergoes fission, right? So let's just figure out what that would be per mole. If we get 2.7593 times 10 to the minus 11 joules, right, per one atom or per one nucleus, right, times 6.022 times 10 to the 23rd atoms per mole, right, we find out that this adds up to 1.66 times 10 to the 13 joules per mole. All right. Remember all of our chemical reactions, right? Do you remember the roughly what kind of energies were associated with those chemical processes?
Like exorendo or?
For just on the ballpark, right? In terms of kilojoules per mole, right? We did delta H's and we got certain values in kilojoules per mole. Roughly how many?
Like 1 to 100.
Yeah,
right?
like a couple hundred. Maybe the really energetic reactions were maybe up to 1,000, right? This is 10 to the 13. So in kilojoules, that'd be 10 to the 10. So that'd be what? 10 billion times 10 billion kilojoules, right? 10 billion kilojoules, right?
Yeah.
So you're talking about a huge amount of energy, right? And that's the source of the energy that you get in fission, right? It's because you lose some mass, that mass gets converted into energy, right? Now, turns out you can take a big atom and break it into smaller ones. And if you look at the masses of the reactions and the mass of the products, you get this lost mass. You can also do the opposite. You can take two small atoms and make a bigger one, and you get the same effect. Notice here, if you take two hydrogen atoms and two neutrons, you combine them to form helium, right? You go from 4.03 AMU to 4.0026 AMU, so you lose 0.03038 AMUs, okay? So again, you lose weight. How is that? Well, turns out there's something called the binding energy. So you can think about the binding energy this way, and I'm just going to describe it to you and see if it makes sense. Let's say you form a helium atom, okay? What is in a helium atom? Two neutrons, two protons, right? So you look at the masses of those four particles, and then you compare it to the mass of the helium atom. And like I said, the helium atom is lighter, right, than the mass. And I'm leaving out electrons here, but the electrons don't really play much of a role, all right? So it's just the nucleus, right? Two protons, two neutrons, add up those masses, and then weigh the helium nucleus, and you'll find out the helium nucleus is lighter, all right? That is true for every element that is stable, right? For every nucleus that is stable, that is in fact the case, right? The nucleus itself is lighter, right, than the particles from which it is made. That difference in mass is called the nuclear binding energy. That's what holds the nucleus together, okay? The highest nuclear binding energies occur at about atomic number 26, all right, or 27. So iron 56 is actually the nucleus that has the highest binding energy. That means that when you put together the particles that make up an iron 56 nucleus, and you compare the weight of that compared to the weight of the particles, that has the biggest change per particle, okay? Which means that this nucleus is one of the most stable nucleuses of all, okay? The iron 56 nucleus. So what does that mean? That means you can take heavier nuclei, which are less stable than iron, and break it into lighter ones, and you get energy out, right? Similarly, you can take lighter nuclei and fuse them together to form heavier ones, and you get energy out. So in other words, on this side of iron, these elements can undergo fusion. In other words, these elements will never undergo fission and give off any energy. Fission would require energy, okay? But they can undergo fusion to get energy. On this side, they can undergo fission to get energy because this is kind of the most stable, most ideal kind of nucleus. Does that make sense? Questions? Sophia.
I was thinking that when you said it had more binding energy, if you broke up iron, it would create more energy. But I guess now that you explain that, it would be the other way around. Like it wouldn't break
Exactly.
up.
Exactly. It would take the most energy to break up the iron nucleus than any other nucleus. Yep. Very good. That's exactly right. Taylor.
I just have two quick ones.
Yeah.
So if you were to like flip this, would iron be like the lowest potential energy? Is that kind of like a way you could think
Yes.
of it?
Yep. You can think of it that way. Yep.
Okay. And then
Yeah.
also, why is there a big spike with helium and lithium? Or is that just the way it is?
Shoot, I don't know the answer to that question. I could try to figure it out, but I don't know why it is. Different combinations are going to give you slightly different stabilities.
Okay.
But yeah, there's definitely some differences there. And part of it, there's other weird things going on, Taylor. Like for example, I think that actually, now that I think about it, it could be because of this. For some reason, there's some tendency towards even numbers. Even numbers tend to have higher binding energies than odd numbers.
What? So weird.
Yeah. And so when you have 3 protons, and I don't know. It's beyond my pay grade, but that's the kind of thing that goes in. I'm not a nuclear chemist, so I don't really answer these things. But
no, that's cool.
But it has something to do with that. That is one of the factors that determines these things.
Yeah.
And so if you look at stable isotopes, the vast majority of stable isotopes have even numbers of protons and neutrons. Obviously, every other element has got to have an odd number of protons, but when it does that, it'll typically have an odd number of neutrons so that the total number is even.
Okay.
And there's lots of exceptions, but generally speaking, even numbers tend to be more stable than odd numbers. Okay, so that means that you can have fusion then as another way. And now the other thing I want you to notice is the steepness of the curve on the fusion side versus the fission side, right? The fission side says take a big atom, break it up into smaller ones. You get the difference in energy between this and this, right? But when you do fusion, you get the energy difference between this and this. And notice how much more steep that is, right? That means that you get more energy. And if you calculate it per gram, it's even more than that. So fusion is actually gives off even more energy than fission does, and especially per gram. So what kinds of fusion reactions are there? So well, you can take deuterium and helium and fuse them together to form tritium, which is heavy, basically heavy hydrogen and a neutron. And that process also is very exothermic and gives off even more energy per gram than fission. So and the nice thing about that is that the products are less problematic, right? Because if you look at this, here's a fission reaction. The product is helium, and the helium itself is not radioactive, right? So this process, if we can get it to work, would be awesome. And we do have fusion reactors where we can get fusion to happen. The problem here is the difference between fission and fusion. Now remember, in fission, what we're doing is we're throwing a neutron into a nucleus, right? So a neutron is neutral, right? And it's going into a positively charged nucleus. So it's relatively easy to get the neutron into a nucleus. When you're doing fusion, you gotta force together 2 positively charged nuclei, right? And they tend to repel each other. So the attractive forces only take over when they get very, very close. So in other words, when you're undergoing fusion, initially they just bounce off each other, right? It's only when you throw them together really, really hard they get close enough that the strong force takes control, and then they fuse, right? So the temperatures required are very, very high. They're so high that there's really no materials that can withstand those kinds of temperatures without melting, right? So you can't just have fusion sitting in some sort of container. So what they've done is they've built these magnetic fields in this thing called a tokamak. And these are magnetic fields that contain the plasma where the fusion is happening, right? And that prevents it from Yeah, you basically have to make a small sun, right? Fusion is the reaction that happens in our sun and in all stars, right? So all stars are basically undergoing fusion all the time, and that's how they generate so much energy. But yes, you have to create a small sun, and there's really nothing to be able to contain it. So you have to contain these magnetic fields, and this requires a lot of energy, right? So at first, they were, the first fusion reactors consumed much more energy than they ever produced, right? But then we got better and better and better, and now we can make fusion reactors that actually produce energy, right? But again, the technological challenges have remained, and this is still not a viable energy source. So we don't have any electrical power plants that create electricity through fusion right now, okay? It's possible, it's very expensive still, and again, this is a sort of a financial, at the end of it, it's a sort of financial situation where you got to be able to create electricity at a price that people will buy, right? And currently this is way too expensive, especially when you have other technologies available. Okay, I see a couple questions. Sophia.
Never mind. I forgot my question.
Okay,
Sorry.
no problem. Sorry. Taylor.
I heard that these like don't melt down like nuclear, like our normal nuclear reactors, because
Yeah,
this is so hot.
I believe there's less of a chance of sort of accidents, because if something goes wrong here, the whole thing just basically stops happening.
Yeah, because the like reaction dies, right?
Yeah,
like, I think
reaction dies. Yep. It's very hard to get this reaction to keep going. That's the hardest thing. Once you have a fission reaction going, it keeps going. With fusion, you got to actively work to keep it going.
And sorry, just one more, but
Sure.
so since it's so hot, the plasma, the heat, like, how do I say this? How do they keep the heat in? Because does the heat emanate, or it's
yeah? So these things are super insulated, but obviously you got to suck some of the heat out ultimately, because that's the heat you need to use to generate electricity, right? So the design is such that this is highly insulated to keep the heat in. But at the same time, there's enough of a leak in here so that some heat can get out and boil water to create steam and then generate electricity.
That's so crazy.
Yeah.
It's like insane.
Ryland.
I think you just mentioned it, but I was thinking about this. I remember when we were talking about fission, part of what's going on is that it's essentially creating the materials it needs to continue the reaction.
Correct.
Is that something that takes away from the viability of fusion, that it's not creating its own sort of?
Well, in a sense, what the fusion reaction is creating is the heat that allows it to continue, because what this feeds off is heat, right? It needs those very high temperatures for these collisions to happen, right? Because this is positively charged, this is positively charged, they got to collide with each other. That requires very high temperatures. Once you get it going, the heat that it produces will induce more fission. So for example, in a hydrogen bomb, right? So in a hydrogen bombs are built off fusion. Atomic bombs are built off fission, okay? We've never, a hydrogen bomb has never been used in a war, but we have thousands of them in our arsenal in the United States, and other countries have them as well. In a hydrogen bomb, what happens is that they're called two-stage nuclear weapons. So the first stage is actually an atomic bomb. The atomic bomb creates enough heat for fusion to happen. And then that causes the second stage, which is the fusion. And then the fusion itself creates enough heat to keep the fusion going, right? To create an explosion. Does that make sense?
Yeah, that makes sense. So they both sort of feed into their own, like their own propagation, just in different ways, sort of.
Yeah, but a fusion bomb is a little more like a chemical reaction, in the sense that, for example, if you just have gasoline, it won't burn until you create a spark, right? Because it needs a certain amount of temperature to get over an activation barrier, right? But once it starts to burn, the heat that it produces will increase the temperature enough for it to continue to burn. So it's that same idea.
Cool. Thank you.
Yeah, absolutely. There's not a critical mass for fusion the way there is for fission. There is a critical temperature, right? But there's not a critical mass. Okay, so what else? A couple medical applications of radioactivity. When we started this section, I talked a little bit about my scan for infection in my appendix, right? So that's one kind of medical application. Let's see, do I have so that's like a bone scan like this. So basically they can give you, doctors can inject into your body antibodies, for example, or other kinds of materials that are tagged with radioactive isotopes, right? And the idea is that depending on where those things go, like for example, antibodies will go find infection, right? So wherever there's infection in your body, it would radioactively decay and you could detect where that infection is, right? Other things are like bones, for example, so they can give you radioactively tagged substances that will concentrate in your bones, right? And then they'll be able to get a scan of your bones that way, right? So scanning or diagnostic applications are one group of applications for radioactivity. You can also do treatment with radioactivity because radioactivity damages biological molecules, right? And it damages things like cancerous tumors, for example, right? So this is gamma ray treatment where they'll put gamma rays and focus that on a tumor in the body, right? Now the problem is, let's say, so here's a human being, right? Let's say they have a tumor there. So you put in the gamma rays like this, right? And then that will kill the cancer. Now it's more effective at killing cancer. It turns out it's more effective at killing cancerous cells than your own healthy cells, but it does also kill some of your own healthy cells, right? So to minimize that, what'll happen, and you can see this thing can kind of rotate, right? Why does it rotate? Because the idea is you go from many, many different angles, right? And you maximize the exposure to the cancerous cell, but you minimize the exposure to healthy cells, right? Gamma ray treatment is the main radiation treatment that they use for cancer. There are others, but gamma ray treatment is the main one. Okay, so those are the main things: diagnosis and then treatment for cancer. Now, radiation has risks associated with it, right? So, you might ask yourself, well, why in the world would they treat you with radiation, right, which kills cancer? But at the same time, one of the risks of that is an increased risk of cancer, right? You may think that seems kind of not so smart, but in fact, it's really smart, because at the end of the day, and this is what we're struggling with so much as a country right now with these vaccines. I mean, it's a risk-benefit analysis. It's always that, right? So for example, if you had the choice of 100% chance dying of the cancer you have, right? Or you can treat that cancer, but that'll increase your risk of future cancer by 3%. Right? Which one do you choose? You don't, if you have cancer, you don't have the option of choosing neither. You got to choose one or the other, right? So that's why you choose to have the radiation treatment, even though that increases your risk of a future cancer by 3%. But if the cancer that you already have is going to kill you, right, you'll take that risk, right? Because it's a small risk compared to the radiation risk, right? And a lot of times that cost benefit analysis is something that scientists understand and grapple with all the time, right? Like we're doing right now with the Johnson & Johnson vaccine, but the general public doesn't often really understand that, right? So, would you take a chance of 1 in 10 million, right, of a blood clot versus a chance of 1 in 100 of dying from the thing that the Johnson & Johnson vaccine prevents, right? That's the kind of analysis that has to be done. Okay, so what are all the risks from radiation exposure? Well, acute radiation damage. Basically, if you're exposed to radiation, it kills cells, right? And so it'll kill it'll kill cells indiscriminately, but it tends to kill rapidly multiplying cells more efficiently than those that aren't as rapidly multiplying, right? And so that's why cancerous cells are killed more efficiently than normal cells, for example. But it does kill other cells, and you can have acute radiation damage, which basically makes you very sick and can kill you just from, and that happens immediately. So for example, at Chernobyl, there was a bunch of rescue workers that went right in the vicinity of an exposed nuclear core, right? And they were immediately bombarded with radiation. They got radiation sickness and died within a month or two, right? So that's really bad. Now, the only place really where you can have that kind of damage would be an exposed nuclear core or a nuclear explosion, right? Even if we had something that was radioactive right here, or if you had that near you, that wouldn't create this kind of damage. This is very, very intense. You need high levels of radiation to do that. Second exposure risk is increased cancer risk. So as we said, right, when radiation damages, interacts with matter, it ionizes atoms. If those atoms are part of DNA, right, then the DNA in a cell gets ionized, it gets changed. Most of the time, that means the cell dies, right? But occasionally there can be a change that causes the cell to replicate abnormally, and that's cancer, right? So increased cancer risk. And then there's also the possibility of genetic defects. So if radiation interacts with reproductive cells like sperm or egg, right, then it can change the DNA in those cells, and then that can lead to genetic defects in the offspring, right? And so we've been able to observe this in laboratory animals. So you expose, when a laboratory animal is exposed to high levels of radiation, right? Yeah, exactly, Teenage Mutant Ninja Turtles. Their reproductive cells get changed, and then you have these genetic defects in the offspring. We haven't really observed this in humans, right? Because of course we don't do these kind of experiments in humans. And there haven't been enough humans really exposed to enough radiation to really see that in humans, right? At least in any definitive way. But certainly these other things have been observed. Radiation is measured in a unit called REMS. And just to give you an idea, 20 to 100 REMS, you get a decreased white blood cells count and possible increased cancer risk. 100 to 400 REMS, you get radiation sickness, definitely an increased cancer risk. 500 plus REMS would result in death. How much are we exposed to? Like you and me just sitting here, how much radiation are we exposed to? We're exposed to about 1/3 of a REM every year, okay? So, it takes 20 before anything measurable happens or anything observable happens, right? Some sorts of medical procedures expose us to more than that, right? So for example, if you're a cancer patient and you're undergoing radiation therapy for cancer, you're doing somewhere in this range, 20 to 100 REM is what it takes to be able to kill the cancer cells. So you do get some of these side effects, right? But again, you take the side effects in order to cure the cancer, right? How many REMS is an X-ray? X-ray is, let me see, I think I have that information here. A 5-hour jet ride is about 2.5 millirem, right? 2.5 times 10 to the minus 3 rem. A chest X-ray is about 8 millirem. So just to give you an idea. How do the rays know how to target cancers? Okay, so the rays don't know how to target cancer cells over regular cells. There's two things. One is that it kills cancer cells more efficiently because they're rapidly multiplying, and cells that are rapidly multiplying are more sensitive to it. And then secondly, by targeting it via different angles, you minimize the exposure of healthy cells and maximize the exposure of the cancer cell. Let's see.
So is it something like they're when they're rapidly multiplying, they're just more sensible to it because they're not mature or something?
So what happens is when rapidly multiplying cells, right, when you damage the DNA in the cell, it really slows down how fast they can multiply. So that's why. So it doesn't like target them any more than other cells. It's just that those cells are more prone to, if they can't rapidly multiply, then the tumor can basically be reduced and maybe even eliminated. Let's see. Megan?
Yeah, in regards to when we were talking about the bone scans,
Yeah.
how do they tag, like we were talking about the antibodies, like where are they tagging that on the antibody? And like,
Yeah, so I don't know the exact procedure, but there's basically a way to chemically attach, for example, a technetium atom to a little snippet of a molecule that will then attach to an antibody. Does that make sense? So you can incorporate some of these radioactive isotopes into small molecules, and those small molecules can be designed to bind to a particular place on the antibody, right?
is it like the antigen?
Pardon me?
The antigens?
I don't know enough about the details to answer that question. It might be something like that, but I'm not totally sure.
Okay, thank you.
All right. Good questions. All right. So I think we're done with that new material. Are there any other questions on any of this? I have one more thing I want to do today before I let you go, but are there any other questions on any of this? Sophia.
I know that it's harder to get fusion, but is there more atoms that would be possibly undergoing fusion than fission? Or is that?
Well, so fusion can work off basically hydrogen, right? And there's enough hydrogen in water for us to, if we could get fusion working as an energy source, it would solve our energy problems for, I don't know, thousands and thousands of years. I mean, you know, fission itself requires uranium, and the uranium deposits that we have are limited. And so, you know, fission will eventually run out. I mean, I think we, at current rates of consumption, you know, we have enough uranium for maybe 100 more years of fission, and then it runs out. I mean, we have problems with all of our current sources. Fossil fuels will run out, and depending on which fossil fuels will run out in 50 to 60 years. So no matter what, we have to change our energy, where we get our energy. And the ultimate solution, of course, is solar and energy from the sun. And it certainly seems like we're going in that direction, either direct or indirect solar, because wind power is basically an indirect source. Yeah, the average person, you know, is exposed to about 1/3 of a rem every year, right? And that's from, you know, where you're sitting right now. There's radiation coming in and out of the ground. There's radiation coming in from outer space, and we're all exposed to that all the time. When you go in a plane, you get a little bit above our atmosphere, and you're actually exposed to a little bit more, right? When you go get an X-ray, you get a little bit, right? So, but from natural sources, it's about 1/3 of a rem. Taylor.
Does the REM exposure have some kind of time associated with it, or is it like 500 and like that's the peak?
That's a single dose exposure. So those numbers that I was showing you there were single dose, right? So this is a single dose exposure of this much produces these effects.
Okay. Okay.
Yep. All right. Very good. Oh yeah. So when you get an X-ray, you know, for example, they'll put a lead shield on places where they don't need to image, right? Because again, you don't want to expose things that you don't need to expose. You want the exposure. So for example, if you're getting a dental X-ray, right, they just want to see your teeth. They don't have to expose your chest and the rest of your body. So they'll give you like a lead vest to put on, right? That'll protect it and keep you from getting exposed in other places. Again, the risks of those kinds of exposures are very, very tiny, but they're so small that they're not even measurable, right? You don't see anything until, you know, you get to about 20. So, but still, the idea is, you know, if you can make the exposure zero, make it zero, right? But If you need an X-ray, the benefits of an X-ray far outweigh the risks, right? Because if you keep your arm broken, right, you're going to be damaged for life, right? But the chances that an X-ray is going to do anything in terms of increasing your cancer risk is pretty much zero. Right? They go through. Gamma rays go through. In fact, I didn't really talk about this, but I should have. If you look at the different kinds of radiation, you can talk about something called ionizing power versus penetrating power. And ionizing power is alpha is greater than beta is greater than gamma, right? So in other words, in terms of its ability to create ions and do damage, an alpha particle, since it's like 2 protons and 2 neutrons, the heaviest one, right? It's kind of like the Mack truck of radiation, right? When it hits other cells, boom, it does a lot of damage, okay? Beta particles are a little smaller, right? Well, a lot smaller. When they hit molecules, they do less damage. And then gamma radiation does the least damage of all, okay? But when you look at penetrating power, they're exactly the opposite. Gamma is greater than beta is greater than alpha, right? So if you think about this one as being the Mack truck, and this being sort of the, the 4-door sedan, and this being the moped, right? Then the moped is the one that's going to be able to penetrate the furthest, right? It's going to be able to get through a traffic jam, and right? So it's going to be able to penetrate the most. It can go right through matter, right? It can go right through your body, right? Beta particles are going to be the next most penetrating, and then alpha particles are going to be the least penetrating. So for example, if we were in a classroom and I had an alpha emitter in the front of the class, you would be exposed to very little radiation because the alpha particles that were coming off would mostly be absorbed by the air, right? Between you and me, right? Because the air is like a big traffic jam, right? And as the alpha particle goes through, it's so big that it can't get through it. Now, if I had a gamma emitter, not only would you be exposed to those gamma particles, but the people next door would be exposed as well because it would go right through the walls, right? Go right through the air and right through the walls, right? So, so most medical treatments of the ones I'm talking about, for example, for diagnosis, use gamma radiation, right? Because for example, for diagnosis, you want it to get out of the body, right? We're creating the least amount of damage, right? So that's why you would use gamma, right? There are some sorts of radiation treatment that use other forms, but they're more rare. Sophia.
Sorry, per your comment, I understood that like uranium is the only element that we can get fusion from.
There are fission, uranium-235 undergoes fission. There are others as well, but that's the main one.
Okay.
But there are others that will undergo fission as well, other nuclei, other than uranium-235. In terms of uranium, that's the only isotope of uranium that will undergo fission. So uranium-238 will not.
And just because of, and I think you talked about this, but is it because of the binding energy or?
No, because the binding energy is not that difference between the two of them. It has to do again with this funny magic in the nucleus of having odd numbers and even numbers and what makes a nucleus stable and what doesn't make it stable, right? So when you take a nucleus of uranium-235 and you add a neutron, it becomes very unstable, and that's why it fissions. But if you took uranium-238 and added a neutron, nothing would really happen. Okay, awesome. Okay, I wanna, since this is our last day really of new material, I wanted to just end with a little parent-like advice. So this is what I call my life rules, all right? And, this is just for fun, but it's also because I hope throughout this year, that you've been excited by learning a little bit of chemistry. I obviously love it. I hope you've grown to love it a little bit as well. But I also want you I also want to give you just a little bit more advice as you leave. I probably won't have you again as a student. I do hope I get to meet you in real life someday, especially those of you that I've kind of gotten to know. I would really appreciate it if you look for me in the fall. I'm going to be on campus if they'll let me. I think they will. I think we'll be, so find me. My classes are all scheduled to be face-to-face, and you can look on the schedule and see where I am at what time. And if you happen to be on campus and if you can come by and say hi, I would really appreciate that. But anyway, here are my life rules. There's the top 10. So we'll do it like a top 10 list. So first life rule, chase adventure because life without adventure is mere existence, right? So get out there and travel if you can, right? If you can, while you're in college, if you can do a semester abroad or a semester in some other place, right? Those are life-changing things. I was lucky enough to be able to take my family and spend a year in Madrid, Spain, mostly because my family is from Cuba. And so I spoke Spanish. I wanted my children to learn Spanish, and I wanted them to get a little bit of that. And so we did that, and it just changed our entire family. It was a life-changing event. But travel if you can, spend some amount of time somewhere else. Go explore the wilderness if you can't do other things. There's so much adventure out there to be had, and you got to somehow balance your life and make sure you include a little bit of adventure in it. This is my wife mountain biking with me in Moab, which is a really amazing place. Rule number 9, balance contentment with ambition. And you know, I tell my kids this all the time. You know, if you're content watching Netflix all day long, and that's your life, that's not a really very great life, right? And if you're so ambitious that you can't sit down one evening and watch a show on Netflix, then that's a pretty sad life as well, right? And so there has to be a balance between those two things in all of our lives. And some people will find the balance in different places because we're all wired a little bit differently, right? But ultimately, everyone has to find their own balance when it comes to contentment and ambition. And I don't know if I've talked before about E.B. White, one of my favorite authors. He has a really great book on writing called The Elements of Style. If you want a little book on writing, you should buy it. But anyway, he's the author of Charlotte's Web and The Trumpet of the Swan and a bunch of other children's books. And I love this quote from him. He says, "If the world were merely seductive, that would be easy. If it were merely challenging, that would be no problem. But I arise in the morning torn between a desire to improve or save the world." That's the ambition part of it, right? And I don't mean necessarily ambition in terms of financial ambition or anything like that. I mean ambition to try to save the world, right? Or improve the world. And you guys are all getting educated because you have at least some of this ambition in you, right? You want to improve or save the world. And a desire to enjoy or savor the world, right? That's the other side of it. That's the contentment side of it. And this makes it hard to plan the day. I love that, right? All right, 8, choose courage over fear because fear paralyzes and courage overcomes. So this is one that I personally struggle with myself, mostly because I think I got a little bit of a fear gene from my father. My father left in the middle of his life, was thrown in jail. My mother and father are from Cuba. In the middle of their lives, they had 2 girls in Cuba. They were thrown in jail by the government, right? For a crime my dad didn't commit. And he was a friend of his got him out of jail, gave him his passport and said, "Hey, take your family and leave tomorrow and don't take anything with you," right? And so my father and my 2 sisters and my mom left Cuba sort of with nothing, right? But that experience really jaded him, right? And I think it haunted him the rest of his life because right there in the middle of your life, you just get everything changes, right? And so I think I inherited a little bit of that. But anyway, so every time I can, I always try to choose courage over fear. And that doesn't mean I do stupid things, right? Like I don't hang glide or jump off a cliff or anything like that. But I try to be courageous in my decisions, right? And I try not to let fear dominate my decisions, right? And because fear will paralyze you, right? But courage can overcome things. This is one of our favorite runs in Mammoth. It's over by what's called Dragon's Back. Any of you snowboard or ski Mammoth, this is one of our favorite places. Realize that deep pleasures require deep, deep effort. So there are some things in life that are just hard, right? But they can be very deeply satisfying. So for example, learning another language, right? Learning another language is really hard. It requires a lot of commitment, but in the end, it's really satisfying, right? And some of the things that will give you the most satisfaction also require the most amount of work, right? And somehow you have to find that balance as well, right? And it's often too easy. Circumstances will push us to the easy over the good, right? That one little thing that all those little things that aren't that important, but are constantly sort of begging for our attention versus the one bigger thing that requires more effort, but in the long run really is satisfying. Listen to your emotions, because emotions can summarize multiple inputs of which the conscious mind may not even be aware. So I know some of you are making things like college decisions right now in terms of where you're going to go after City College. And, you know, there's one part of that that's very logical, right? You write down, you make a list of benefits and perhaps setbacks or whatever. And you try to analyze it really logically. But at the end of the day, listen to what your gut is telling you, because a lot of times your gut is putting together a lot of things, a lot of inputs, right, that you're not even totally aware of. So don't write that off, right? That's a very important source of information that we all have, that we've evolved to develop, right? And it's telling you something, and it's telling you something that could be pretty important. 5, follow passion, not money, because passion is ultimately what drives success. So a lot of times I'll get students telling me, oh, you know what, I really want to be such and such. I really, really want to be a surgeon or whatever. And then, you know, we'll get to talking and they'll say, oh, but gosh, really, I really hate my chemistry and my biology class, right? I can't wait to get these over with, because then, you know, I can do what I really want. I can really be a surgeon. And so the thing is that if you hate chemistry and biology, you're probably going to hate surgery, right? Because there's a lot of science involved in being a surgeon. There's a lot of biology involved in that, right? And so you always got to first find what you love, right? What are you passionate about, right? Your ultimate vocation will happen if you can put together 3 things, right? Something you love, something you're good at, and something the world needs done, right? If you can find the nexus of those 3 things, right, you will have a very satisfying working career, right? Because you'll be doing something you love, something you're good at, and something the world needs done, right? And that's what you got to follow. And that passion will lead to success, right? But if you just chase success on its own without the passion, it's much, much more difficult to achieve. Choose your friends based on common interests, right? Choose your partners based on common interests, right? Common interest is what holds people together, right? Too many times we choose our friends and our partners on other criteria, right? How do they look? Are they in the right crowd? Do they hang out with the right people? Blah, 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 right? All those sorts of things. We face pressure to choose our friends and our partners in that way. That's a bad way to choose friends and partners. And usually those kinds of friends and partners don't last, right? The inner ring is always so tantalizing, right? Oh, I want to be in that group, right? But the inner ring is really hollow, right? The inner ring is really hollow. True friendships, true relationships are built on common interests and common values. So find people that have common interests with you, common values with you, and latch on to them, right? And develop your friendships that way. Indulge your senses, because everything, all the beauty that's around you comes into you only through your senses, right? We've learned a little bit of things about light, right? Light, how does the outside world get into your brain? Through your sense of vision, right? And it's photons that hit your eyeballs, right? And then create an image in your brain. Or, sense of smell, right? What is that? Molecules that given off by a flower and find their way into your nose, which then triggers a reaction in your brain. Everything, your conscious experience right now is being driven by what's coming in through your senses. So feed that, right? Go look at beautiful things like these flowers. Go to beautiful places. Listen to beautiful music, right? Turn on light that candle in your room that has a beautiful scent, right? I in my house, I keep music on almost all day long. I just love to constantly hear it and surround myself with that, right? It makes a difference because what goes into your brain comes in through the senses. So if you feed those senses good things, your brain will be a good place, right? Super, super important. Stay fit because life requires motion. I'm a little older than you guys, but I really try every day to move my body, right, and get some exercise and stay fit. And I look at some of my friends who are my age that haven't done that, and they just can't experience life the same way. It's much more difficult. And then lastly, find someone you love and love them well. This is my wife, and we're kind of dressed up here for a party. But the Beatles were kind of right. It's not everything we need, but it's pretty important. So anyway, those are my life rules. Thank you for a great semester. I love you guys. I hope to see you around. We're not quite done yet, but we're very close. Again, we'll review on Monday, and then Wednesday will just be an answer session. Okay. Thank you so much. Have a great day. Okay. I'm going to end my class there. I'll stick around for questions if you have any.